Welcome. At this point, we have been discussing the derivative quite a bit, and we've been using our formal or our limit definition of a derivative. So at this point, we're going to begin discussing our differentiation rules, or maybe our shortcut rules. At a certain point, after solving many of these long drawn out limit definition problems, we start to realize there are some patterns. Okay, so in this video, we're going to move away from that definition and we're going to begin talking about some of our shortcut rules. The first rule we have is the derivative of a constant function. All right, so if we have a constant function, f of x equals some constant c. So constant function looks like a horizontal line. Now remember, derivative, that word derivative means rate of change. And what is the slope of a constant? The slope of any horizontal line is going to equal 0. So the derivative of f of x equals some number c. So looking at this, the derivative of f with respect to x of that constant function, or taking the derivative with respect to x of some constant value, is always going to equal 0. So this is a rule that we know and we keep and we use. Another rule that we use quite a lot is our power rule. And the reason this says general version is because the book identifies two different versions of the power rule. So if we have n, this n value, if n is any real number, so this is to say we have some function f of x equals x to any number, x squared, x cubed, x to the fifth, x to the negative 10, all right? So the derivative, taking the derivative with respect to x of some variable x raised to a real number n power, that is always going to equal n, so that power comes in front, times x raised to the n minus 1. We'll subtract 1 from that power. And so when we are taking the derivative of any x raised to a real number power, we're always going to apply this property where we take that power, n, we pull it in front, and then we subtract 1 from the power. So let's do a couple of examples looking at these two rules. If I asked you to take the derivative with respect to x of any number, say 3.7, that is a constant. The derivative of a constant is 0. The derivative with respect to x of pi is a constant number. It's an irrational number, but it's a constant, 0. The derivative with respect to t of this constant, say e, could be 0. So e is a number, Euler's number, 2.718 approximately. Notice I said take the derivative with respect to t. We could have a different variable with which we are differentiating with respect to. I could say the derivative with respect to u of some number 107. Again, in all of these situations, we're taking the derivative of something that is a constant, and the derivative of a constant is equal to 0. So the derivative of a constant is 0. Remember, derivative means rate of change. Constant function is a horizontal line. Horizontal lines have a slope or rate of change of 0. All right, so considering our power rule, the derivative with respect to x of x to the 10th, that would become 10, that power 10 comes in front. So we have 10x to the 10 minus 1. This is going to become 10x to the 9th. We could say the derivative with respect to x of x to the negative 3. So again, I'm looking at this, I've got negative 3 is my real number in the power. So I have variable x, I'm taking the derivative of x with respect to x, notice these variables match, this is going to become negative 3x to the negative 3 minus 1, or negative 3x to the negative 4th. And keeping in mind, we know properties of exponents, that negative exponent could be rewritten negative 3 over x to the positive 4th. So these last two notations here, these two guys, mean the same thing. They're just written differently. I could change variables. I could say, all right, well, let's take the derivative with respect to s of s to the negative 2. So the derivative with respect to s of s to the negative 2, negative 2 is my power. That's going to become negative 2 s to the negative 2 minus 1, or negative 2 s to the negative 3. That's also equal to negative 2 over s cubed. So those last two terms are exactly the same. Let's just look at one more here. The derivative with respect to q of q to the 1/2. So notice I have a 1/2 power. It's a real number. It's just a rational power. And then again, I've changed my variable from x to q, but I'm taking the derivative of q with respect to q. This means take the derivative with respect to the variable q. So in this situation, I will have 1/2 q to the 1/2 minus 1. That is the same as 1/2 q, 1/2 minus 1 is negative 1/2. So this is the same as 1 over 2q to the positive 1/2, or 1 over 2. Remember, q to the 1/2 is a square root, so 1 over 2 square root of q. And both of these two answers here, these are both correct. In this case, if I was dealing with my math lab, I would return my answer like this. I started with a positive rational exponent. I'm going to end with a positive rational exponent. All right, so let's look at one more rule in this video. So now that we've talked about the derivative of a constant and we know our power rule, we're going to say we have this derivative constant multiple rule. And all this says is if I have some u, and all u represents, u is a differentiable function of x. So that means u is f of x, we can take the derivative of it. If we have some constant c, right, this c is a constant, if I'm taking the derivative with respect to x of some constant times u, I can pull that constant c out in front, and then I have taken the derivative of u with respect to x. I'm taking the derivative with respect to x of u. That gives me the derivative of u with respect to x. I could think about writing that a different way. If I had d dx of some constant times the function f of x, that's the same as pulling the constant in front. I'll use the color here. Pull the constant in front, and I have then d dx of f of x. So this would be that constant times f prime of x, right? So if you have a constant multiple, leave it there and just take the derivative of the variable portion behind it. So let's look at a couple other examples here. So we're going to take the derivative with respect to x of 8x to the 5th. So 8 is a constant. It's a constant multiple. That is the same as writing 8 times d dx of x to the 5th. So, using my power rule here, that's going to give me the 8 would remain, and the derivative of x to the 5th, that's going to become 5x to the 5 minus 1. And this would simplify. 8 times 5 is 40x to the 4th. All right, let's look at another example. You might be asked to find the derivative of y equals negative 2x to the 3/2. So the negative 2 would remain in front. That would be the derivative of y with respect to x is negative 2. And then I'm only going to deal with taking the derivative of x to the 3/2. So that would become 3/2 x to the 3/2 minus 1. This would simplify, multiplying negative 2 and 3/2. That's going to give me negative 3x. And 3/2 take away 1 is positive 1/2. Now, this is the same as negative 3 square root of x. So we have learned our constant derivative rule, our power rule for differentiation, and we've learned how to handle it when there's a constant multiple. I'm essentially done in this video, and I know it's getting on the longer side, but I want to add just a couple more examples of taking the derivative of terms raised to a power. So all these examples, I'm going to be finding the derivative. So we'll say given y equals x to the square root of 3. If we're asked to find the derivative of y with respect to x, so square root of 3 is my power. Square root of 3 is going to come in front, and I have x, that would then be to the square root of 3 minus 1. And I really can't clean that up or make that look any nicer, so we would leave our answer like that. Maybe we have f of x equals 1 over x to the 7th. Now this is not x raised to a power. Right now this is a rational expression, 1 over x raised to a power. What we want to keep in mind though is this is the same as x to the negative 7th. So I use a little bit of algebra to rearrange my problem. In this case, f prime of x, my derivative, that would be negative 7x. Negative 7 minus 1 is negative 8. And since I started with a positive exponent and that x was in the denominator, I would take this one step further and I would say, okay, well, f prime of x, that's the same as negative 7 over x to the 8th. All right, so both of these notations are correct, but dealing with the computer, I would input my answer as this answer that I've put in the box here. All right, let me just do one more. G of t equals, we'll say, the cube root of t. So again, this example isn't exactly a variable raised to a power when we're looking at it. But I can rewrite that. I can say that g of t is t to the positive 1/3 power. We know that the nth root of any variable or number would be x to the 1 over n. So that's a radical turning into a rational power. So if I were to find my derivative, g prime of t, that would be 1/3 t to the 1/3 minus 1. G prime of t is 1/3 t. 1/3 take away 1 is negative 2/3. This is fine as the answer, but if we want to go and make it look as though we started, we could say, well, that's 1/3 t to the 2/3, or rather g prime of t is 1/3 cube root of t squared. And just for good measure, because I love doing examples, I'm going to do one more. So our very last example here, we're going to find the derivative. Y equals -5 square root of x. So the derivative of y with respect to x, that constant multiple -5 is going to stay in the front. Now, square root of x, keep in mind, this is same as writing -5 x to the 1/2. So I'm taking the derivative of x to the 1/2. That would be 1/2 x to the 1/2 minus 1. In this situation, the derivative of y with respect to x would be -5/2 x. 1/2 minus 1 is -1/2. And that's the same as -5 over 2 x to the 1/2, or -5 over 2 square root of x. All right, so I hope that helps you with using the power rule. And really the only way to get better at this is to practice over and over and over again.